Hey everyone. So today was the MEWC DACH versus UK round, and I got to use a Lambda I've been working on for some time now, and it worked really well. So I was really glad of it, and I decided I wanted to share it. This Lambda is called, well, for now, dpathmap, and it's a Lambda that will allow us to calculate distances from a point in a map to other points when minimal distances, when the cost of moving through each cell is variable. Yeah, and also cells can be blocked. So what do we got here? This is the map from the UK case, yeah? And over here we have just the distances, yeah, the cost of moving through each cell. Over here we have London, yeah. So what are we gonna build? We're gonna build the formula, and this goes equals the path map. And then what we wanna do is we're gonna give it the whole map of distances, which I've named cost map. And then we want the row and the column of the initial cell, which I have over here, London, the address, the row and the column. We're going to give it that. And Lambda was able to move diagonally. So we have that fourth argument, diagonals default true. So we're going to keep that as is, just leave it out. And then enter. We give it a little bit. And there we go. There is our map. Yeah. And you can see London over here is 0. And as it gets further and further away, it becomes bigger and bigger and will eventually turns into all these all these values that are too big to show in the cell size. Yeah. And if we wanted to know how many bananas it took to get from London to Belfast, we'll go equal index. We grab this whole map, yeah, and then we give it the row and the column for Belfast, and that times 1,000, and we have 108,000 bananas, which was the answer for bonus 4, right? Um, what else? Over here, I have a random map that has been created with some intention to it to create like an interesting look at how one might move through this map. So what we're gonna do is equal the path map, grab the whole map. We're gonna start at cell 2525, and we are going to disable the diagonals because the result is just more interesting looking. And again, this is a 50 by 50 map. You can see it took it like what, 3 seconds. And you can see how it works, right? If you wanna, go west, then that would be cheaper. Going east, more expensive. This corner over here gets very expensive. You have all these X's in between. These are impassable cells. Yeah, so it's handling it perfectly. Yeah, like for example, from here you got a 50. You would probably sort of more quickly reach over here. You got a 91. If you could go through this X, you cannot. Therefore, this distance is quite big. Yeah. So that is the Lambda. Let's look a little bit under the hood now. Over here is the code for the Lambda. We have these 4 inputs, you already know. And then we define some previous variables. First of all, the diagonals, just a regular if is emitted, blah, blah, blah. Then the row and column directions. Yeah, these are the arrays to check on neighboring cells, depending on whether diagonals are enabled or disabled. Yeah, so in this case, this would be the cell above, the cell below, left and right. Yeah, the row index and the column index. Then the number of columns and the number of rows in our distance map, an NA value, which I use later, a map of addresses. This is also a Lambda of my own. You just give it a map and it's going to return a map of the same size, but with the number of the rows, and the same for the number of the columns. And if you concatenate that, then you have an address map, location map, yeah, that we use later to look up. And then you got your initial map, which it's a bit of a weird formula, but it's made so because this actually can receive multiple starting points simultaneously, which was not really intended. It just turned out that way. I was like, yeah, might as well. So what this formula is doing is if the location in the map is a starting point, then its value is going to be 0. Otherwise, it's going to be x. Yeah. And then we go into the recurring lambda proper. So you have three arguments. You have pmap. Pmap is your constantly updated map of the distances, your path map. You got frontier. Frontier is your list of cells that you are whose neighbors you will be checking for updated distance values. And you have an n, which is an iteration indexer. It's not used for anything, but I find it really useful to keep around for debugging. It's so you can like set an exit condition if n equals 1, 2, 3, and you can check under the hood. So I like to keep it around. And then let's see what the Lambda does. First, we're gonna get our list of row and column addresses. How do we do this? Well, this frontier argument, it is a matrix with 3 columns. Yeah, the first column contains row addresses. The second one contains column addresses. The third one contains distances from the center. Yeah, so if you'll have noticed row deers is a row, and this is a column. So you add them up, and you get the whole combination. You set it to a column, again for the columns, and then the distances. Yeah, you're gonna get. We're indexing our new map. Yeah, for the row and the column. Plus, these are all zeros. Yeah, because we want this column to have the same number of elements as this 2, and to match, obviously. So once we have that, right, we're gonna have a list of all the neighbors and the distance, repeated distance of all these frontier cells. And then we create our new frontier. So first, what we're gonna do is we're gonna check whether we're not out of bounds. If we're out of bounds, it's NA. This is the empty answer, essentially, that I had before. If we are not out of bounds, we're gonna check if the new cell that we are looking at is maybe non-numerical. Then it's also NA. We cannot move through there. Yeah, and this is done after the out of bounds, because otherwise this could get errors, or it could get arrays in sizes we do not want, right? If you index something and you toss in a 0, then you get problems. And then finally, you get the if, whether we're going to update the distance of this cell. And the way we do this is we check if the cost of moving into this cell plus the cost of the current frontier cell that we're looking at the new cell from is lower than the current value of that cell in the in our updating map, our path map. And if that is the case, then we're going to add a new element to our frontiers list, our new frontiers list, which will have the row, the column, and the new distance for that cell. Otherwise, we add an NA. And the idea here, right, is that we check all the frontier cells, all the neighbors for all the frontier cells. And all those neighbors that get updated, there are new frontier cells. And this iterates until we have no more frontier cells. right? So what do we do next? First, we're going to sort them by the distance column, smallest to largest. And then we're going to get the position, yeah, of each unique location in this list. Because you could be looking at a new frontier cell from two different old frontier cells, and that could give you different values. And we want the first one, which is going to be the smallest since this is sorted. Yeah. And then we're going to use that to filter. So what we're doing is we're indexing, with that position and all three columns. And then we're also filtering because we want the first column to be greater than 0, which is going to remove all these NA values, which are worthless, right? But you need them to make the thing just flow. Once you have that, we're going to build our new path map. And our new path map is essentially, if we go a bit from the center outwards, yeah, we're going to do an X match, sorry, of this this location location sequence, yeah, into the first and the second columns of this new frontier list combined, right? And then we use that to index this new frontier list on the third column. So what we're doing here is we're going to get a map. Oh, yeah, with this, there's going to be either errors or the new value, the new distance value assigned to these cells, to these new frontier cells. And then we test that into an error with the old map, right? So the values that were errors were values that were not updated, so they stay as they were. And the updated values, well, they updated. And this looks a bit weird, but it's by a mile and a half the fastest way I've found to do this. I've had many versions of this Lambda, and it used to crash with a 40 by 40. And now it handles it in like 2 seconds less. Okay, so you have your map, and then you have your it calls on itself again, right? You have your exit condition. If the sum of the filtered frontier is 0, then just output the map. Otherwise, call on yourself again with the new map, with the new frontier list, and with the updated indexer. And then we just call on it, right? And it returns the result. So that's how the Lambda works. It can get a bit mind-boggling. Trust me, I know. But it works a treat. So let's see what it can do. The heftiest, I think is the word, map case that I've ever had to work with is the Temple of the Golden Idol by Brian Wright. And specifically, this was played on the, I actually got to play it on the semifinals last year. It got pretty heavy towards the end because you had Temple 3, which is this, which is a 100 by 100 map. If you don't know this, what we are aiming to do here is all these bricks, they're impassable, right? And these are your terrains, these are your starting points, your terrains, and you get to these golden idols. And depending on which animal you're assigned, you will go through, each of these terrains will have a different cost. So, and this is actually, I have this table down here. Yeah, you have like an eagle, for example, it's a 7 years. Everything. Frog can swim very quickly or go through the marshes, but grasslands and deserts are complicated, that kind of stuff. And doing this with your typical circular reference formulas it was the way to go at that moment, at least for me. But it still took a while, right? You had to set it up, and you had to set it up for every single animal, yeah. And then the way this was asked, you started going through one exit, then exiting through another. It got complicated. Yeah. Uh, so let's take a look at what this lambda thinks of this starting at the center, yeah, and then with an eagle. Because if you start at the center and you go out, then the value at each of the entrances is actually the cost of getting to the golden idol from that entrance. Let's do that. And I've pre-built this lambda. You can see let our cost map is we're indexing cost by X matching the eagle to animal, which is just the range that the named range I have for that. And then we're X matching the whole temple, yeah, to the terrain. And then we're gonna do the path map with that. And we're starting at cell 5050, which is pretty much in the middle. And you cannot take diagonals. So you click equals and that. And after just a moment, you have, and again, I have conditional formatting here to look at the values. You start here at the center, which is red. And as you can see, actually, let me set this to 20%. You get the you roughly you can see how it goes higher towards the exits. And each one of these exits, yeah, this is like if I started on this cell and I wanted to get to the golden idols, my cost is 4410. Yeah. So the way you would solve this case actually for the later ones is you have all the entrances here, right? With the address, the row number, the column number, and I have all the animals here. And what you would want is to create this table where it says, hey, from this cell to the golden idol. Because if they ask you to get to the golden idol and then to exit through another cell, then you just sum the value to get to the golden idol from both of those cells, and that works. Yeah. There's no difference between going in or going out. So what I have here is the same formula that we had before, except that the path map, I am putting it into a variable. Yeah. And then I am mapping into that variable. Well, I'm mapping this the row number and column number -1, right? Because this as you can see, this doesn't start on cell A1 but B2. You have to do -1. And then I am just indexing over this map, yeah, with that row and that column. And as you can see, this will run pretty damn quickly, and it will get you all the answers that you need for this table. I actually think this runs faster than when I did it with my circular reference formulas. So I paste it there and I calculate it. And we're going to give it a little bit. Now this is about 4 seconds each. So the whole table takes you 40 seconds, which on the one hand is not an inconsiderable uh, is not a small amount of time. Yeah. But essentially this, it solved the entire case. I mean, the later questions, right? Because whatever they're gonna ask you, you're just gonna sum it and just there. It you have all the values, right? So it is it's incredibly useful, incredibly powerful, uh, and I don't know, super reliable. I'm actually quite surprised at the speed that I managed to get it to, right? Obviously, a map like this, which has all this impassable terrain, is way faster to calculate. Yeah, I actually did it. I made some tests, which I'm not gonna put in this video because they're kind of long, with a 100 times 100 map, a random map, and it takes about 20 seconds, starting from a corner, which I suspect is longer than starting from the center. I haven't tested that out yet. And the last thing that I wanna show off here is we have here again the map, but this time, and this is something that I wanted to try, and I got an interesting result. I wanted to instead of starting from the middle, I wanted to start from each of the entrances because I figure, hey, if I start here and then I look here, I should get the answer for how um, what is the cost of getting to the golden idol from that entrance. Yeah. So what we have here is well, the same cost map, yeah, for the same eagle, and then you got your dpath map over that. But I am giving it the whole set of addresses from over here, from distances. Yeah, because as I mentioned, this can work with array inputs. So we're gonna let this calculate. There's an error with your formula. What error does my formula have? Oh, there we go. That, I think that's it. Yeah, that's definitely it. Yeah. And if we zoom out enough, you'll see that this actually did not turn out at all how I wanted. Because remember, the greener this is, the higher the value. And it's not here. In fact, if we zoom in, everybody here has 3,500. And why is that? Because the shortest route over here, yeah, was 3430. And the eagle takes 70 on every terrain. It's just what the eagle does. So essentially, one of the entrances, the most efficient one, just started pushing back. Yeah, this one. It got here, so and it started pushing back, and you will see the highest, you will see the peaks halfway through the paths, which I don't know, I thought was quite amusing. So, anyways, that's the lambda. I am going to put the code to build it both regularly and by Visual Basic. I like to insert my lambdas via Visual Basic. The code for both of those will be in the comments, and let me know what you think. Bye bye.